Okay, let's start our video on stoichiometry, limiting reactants, and percent yield. By the end of this video, or hopefully already, you should know how to do mole-to-mole conversions, mass-to-mass or grams-to-grams conversions, know how to determine the limiting reactant and calculate the quantity of the excess reactant, and finally determine theoretical, actual, and percent yield using the percent yield equation. From this definition, the relationship between the relative quantities of substances taking part in a reaction or forming a compound, typically the ratio of whole integers, we can take away that when we balance an equation, we have coefficients in front of our compounds, molecules, and those are the whole integers this definition is talking about. Those will be used in a molar ratio in converting between either moles to a different compounds moles, or we even use those for grams to grams calculations. So let's start with mole-to-mole stoichiometry conversions. I would recommend having a periodic table and a calculator out and pausing this video, alright, so you can do the work and then check it against mine. So we start with our word equation. Beryllium oxide reacts with chlorine to produce beryllium chloride and oxygen gas. All I'm looking for you to do here, as you should be able to see below, is write the equation and balance the equation. Go ahead and pause the video and try this. Alright, and when we pick up beryllium is Be. Go ahead and do this in green for you guys. So beryllium oxide. Alright, if we look at beryllium and oxygen on the periodic table, beryllium is a +2 charge, oxygen with a -2 charge, so there should be no subscripts here. Plus chlorine. Now chlorine, we write that as Cl2. Remember, that's a diatomic molecule. And that produces beryllium chloride. Plus oxygen. Oxygen is another diatomic molecule. Now don't forget Cl2 here. That is not just bringing this over. Okay, that is not the case. Remember your ionic bonding rules, and we have a +2 and a -1 charge, and if we do the crisscross method, that's going to attach to the chlorine, and there's an invisible 1 right down here close to beryllium. Alright, now that we have written this equation, we need to balance the equation. So we take a look. Let's start over here with beryllium oxide. Alright, we have 1 and 1 with our beryllium. Okay, we have 2 oxygen, or excuse me, 1 oxygen and 2 on the other side. So we need to make 2. So now we have 2 oxygen, 2 beryllium. That changes. So now we have to add a 2 to the beginning of this beryllium, and we can go back. So we have 2 beryllium and 2 beryllium on our reactants and our product side. We're good there. We have 2 oxygen, we have 2 oxygen. Alright, so that's balanced. Now let's flip. We already know here we have 2 beryllium, and chlorine we have 4, right? This 2 times 2 equals 4, and that's chlorine, so we had a 2 in front of this chlorine, the diatomic on the reactant side, and we're all balanced. Now let's go ahead and do some work. So we have 3.5 moles of beryllium oxide reacting with excess chlorine. How many moles of oxygen can we produce? So we have 3.5 moles of beryllium oxide. Okay, what we want is right here. How many moles of oxygen can we produce? if you see, excuse me, if you see excess anything, in this case it's excess chlorine, all we're saying is we have enough chlorine in this reaction that it's not going to run out. It is not limiting our reaction. Okay, and that should make sense now. If not, we'll get there in limiting reactants. Okay, so we're in beryllium oxide and we have 3.5 moles. And we're trying to get how much oxygen? So all we're going to do is take our molar ratio. What we have, 3.5 moles of beryllium oxide. Okay. And we're going to look at our molar ratio. So I want moles of beryllium oxide on the bottom because I need that to cancel out. And I need moles of oxygen on top. Why? Because that's what I want. That's what I want my product to be. Right? So we always put what we want to cancel out in the denominator. So now I look at my equation and I see, well, I have how many moles using the coefficient of beryllium oxide? Well, right here I have 2 moles of beryllium oxide. That goes down here. Let's go over to moles of O2. Well, there's nothing in front of that O2, which means there's an invisible 1. So all this math turns out to be is 3.5 divided by 2, and that is going to give us 1.75 moles of O2. There's our answer. Okay, so balancing is important because we are using those coefficients in mole to mole, gram to gram conversions. If you think about this a different way, take that 1.75 that you have. If you look over on this side, right here, okay, that 2, that coefficient of 2 is saying in this base reaction, I need 2 moles of beryllium oxide, or 2 molecules of beryllium oxide, to react with 2 moles of chlorine. Alright, that reaction is going to produce 2 moles of beryllium chloride and 1 mole of oxygen. But notice, in this equation, we're given 3.5 moles. And this 1.75 is simply saying that 3.5 moles is 1.7 times greater than this 2. So if you were to multiply each of these coefficients by 1.75 and then just say, oh, okay, well, here that's going to produce 1.75 moles of O2. You get the same answer. So there are multiple ways to solve. I am showing you what our book tells us to do. But if you would like to see how many times greater the moles given are than what is normally in the reaction, you may do that as well. Next, we're going to gram stoichiometric conversions. Let's take a look at our word problem right here. If we react 25 grams of magnesium with excess hydrochloric acid, how much magnesium chloride will we produce? Okay, so once again, I got to take a look. This right here is what we have. And magnesium chloride, this is what we want. Okay. Now, down below, the mass calculations table. Step 1 is balance the chemical equation. Here you are not given a balanced chemical equation, so you do need to balance this equation by yourself. If you are given a balanced chemical equation, then you can hop down and do steps 2, 3, and 4. Alright? But we are not given a balanced equation. So write it, balance it, And then keep in mind steps 2, 3, and 4 because that is how we're going to solve this equation. Alright, so as you can see, I wrote in my magnesium reacts with hydrochloric acid, that's HCl, to produce magnesium chloride. Remember, right here, magnesium has a +2 charge, so that 2 carries down to chlorine, and then hydrogen is one of the 7 diatomic molecules, so that carries a 2 here. But the good thing is, this should not come into play. We only need magnesium chloride and magnesium for this. So, let's look. Step 1. We've completed that. Step 2. Convert mass of reagents to moles of reagents. Okay? Remember, reagents can also mean reactants. They're the exact same thing. So, let's take a look. We have a mass of what reagent? Well, we see we have 25 grams of magnesium. So, 25 grams of magnesium. That's a G. Let's go ahead and try and fix that. Magnesium. Alright. Now, what are we going to do here? Well, to convert grams to moles, we know this is a one-step equation, and we're going to go ahead and say that the molar mass of magnesium is 24.3 grams. And 24.3 grams of magnesium is 1 mole of magnesium. Okay, so we have the molar mass right here, 1 mole on top. If we look at step 2, convert mass to moles. So we see that yes, grams have canceled. We're left with moles of magnesium, exactly what we want. And doing 25 divided by 24.3 gives us 1.02. Well, let's round that up. 1.0288, which we will round to 1.03 moles of magnesium. Okay, awesome. So we have step 1, step 2, done. Let's go to step 3. We're going to use the mole ratio from the reagent to moles of the desired product. Well, we have up here how many moles of magnesium to how many moles of magnesium chloride. Well, we can see that we have a 1-to-1 ratio, right? Meaning I have 1 mole of magnesium to 1 mole of magnesium chloride. So, let's go ahead, set our train tracks up. 1 mole of magnesium to 1 mole of magnesium chloride. And that's going to give us, well, this one's easy. That cancels out, well, 1.03 times 1, and then divided by 1, number's the exact same, right? So we end up with 1.03 moles of magnesium chloride. Now, last but not least, do not stop there. Step 4, convert the moles of products to grams. So once again, this is a simple one-step conversion. You all have done this. This was last unit. You can do this. So let's get a little more space. 1.03 moles of magnesium chloride. All right. And here, our molar mass is going to be on top instead of the bottom like it was in the first step, or excuse me, step 2. So we know that 1 mole of magnesium